Could our universe, with its billions of galaxies, exist inside a black hole? This question, once purely theoretical, now drives cutting-edge research in astrophysics. To explore this idea, we need to understand what a black hole is and how our universe might mirror its structure. Let's break it down clearly and systematically. A black hole is a region where gravity is so strong that nothing escapes, not even light. It forms when a massive object, like a dying star, collapses into an incredibly dense point. This point, called the singularity, warps spacetime, the four-dimensional grid that defines how objects move and time flows. Picture spacetime as a network of coordinates, not a physical surface, twisted tightly around the singularity by its immense mass. The boundary of a black hole is known as the event horizon. This invisible sphere marks the point where gravity becomes absolute. Anything crossing it, from a starship to a beam of light, is drawn inward with no chance of return. The event horizon's size depends on the black hole's mass. For example, a black hole with 10 times the mass of another has an event horizon 10 times larger, as calculated by the Schwarzschild radius formula. Now let's look at our universe. It has its own boundary, called the cosmic horizon. This is the farthest distance from which light can reach us, given the universe's age of about 13.8 billion years. Light travels at 299,792,500 a second. Beyond the cosmic horizon, roughly 46.5 billion light-years away, light hasn't had time to arrive due to the universe's expansion. Here's the key connection. The observable universe contains an estimated 1.5×10^53 kg mass, including stars, planets, gas, and dark matter. If this mass were compressed into a black hole, its event horizon would span about 46.5 billion light-years, nearly matching the cosmic horizon's size. The universe's average density, approximately 1 to 10^7 kilojoules per cubic meter, also aligns with the density of a black hole of that scale. The match is not trivial. It suggests our universe's structure resembles a black hole's. The question is whether this is a coincidence or a clue to our origins. To investigate, we must delve deeper into black hole physics and examine evidence from our cosmos. This hypothesis, grounded in observation and mathematics, sets the stage for a profound scientific inquiry. The idea that our universe might exist inside a black hole hinges on advanced physics. Albert Einstein's theory of general relativity describes how mass and energy shape space-time inside a black hole. This shaping becomes extreme past the event horizon. Space-time curves so tightly that it forms a new region, separate from the outside universe. This region acts like a distinct cosmos, with its own rules and structure. If our universe is inside a black hole, we could be living in this isolated space-time. The event horizon would shield us from the external universe, making it impossible to see beyond. Our observable universe, defined by the cosmic horizon, might be the interior of this black hole. This model suggests our reality emerged from a black hole's core, a concept supported by mathematical solutions in general relativity. To understand this, consider how gravity works. It treats gravity not as a force, but as a curvature of space-time. Massive objects like stars bend this grid, causing nearby objects to follow curved paths. In a black hole, the curvature is so intense that all paths lead to the singularity, a point of infinite density beyond the event horizon. However, equations predict a new space-time, potentially vast enough to house a universe like ours. Recent research offers clues to test this hypothesis. Astronomers have studied the rotation of spiral galaxies, which resemble spinning pinwheels of stars. A study examined several hundred galaxies using telescopes to observe their motion. The findings were unexpected. About 2 out of every 3 galaxies rotated in a direction opposite to our Milky Way galaxy. This pattern was seen in observations above and below the Milky Way's plane. This rotational bias is significant. In a typical universe, galaxy spins should be random, with half rotating one way and half the other. A 2-3 preference suggests a coordinated motion across vast distances. This could indicate that the entire universe has a net rotation, a property described as angular momentum. Angular momentum measures how much an object spins and in what direction. Why do galaxies spin at all? When galaxies form, they start as clouds of gas and dust. As these clouds collapse under gravity, any small motion within them grows stronger. This is due to a law called conservation of angular momentum. A large, slowly moving cloud becomes a smaller, faster spinning galaxy. This explains why individual galaxies rotate, but a universe-wide rotational pattern is harder to explain. If the universe has a net rotation, it challenges standard models. The Big Bang theory assumes the universe expanded evenly in all directions with no preferred spin. A rotating universe suggests a different origin, possibly tied to a black hole. This connection is intriguing, but requires more evidence to confirm. The discovery of a possible universe-wide rotation raises deep questions. In most cosmic models, the spins of galaxies should be random. Each galaxy forms from a collapsing gas cloud with its own unique motion. These motions, driven by turbulence, typically cancel out across the universe. A net rotation, where galaxies prefer one spin direction, suggests an unexpected order. This finding challenges our understanding of the universe's origin. Angular momentum is the key concept here. It describes how much an object rotates and in what direction. For example, a spinning top has angular momentum, which keeps it upright. In the universe, every rotating object from planets to galaxies carries angular momentum. This property arises during formation. As a gas cloud shrinks, its rotation speeds up, much like a dancer pulling in their arms to spin faster. This is called conservation of angular momentum. In a typical universe, the angular momentum of galaxies should balance out. Half should spin one way, half the other, with no overall preference. The recent study of several hundred spiral galaxies found otherwise. About 2 out of every 3 galaxies rotated opposite to the Milky Way galaxy. This bias, observed across vast distances, hints at a universe with net angular momentum. Such a pattern is not expected in standard models, like the Big Bang, which assumes uniform expansion in all directions. This rotational bias connects to the black hole hypothesis. Black holes preserve only 2 properties from the matter they consume: mass and angular momentum. When matter falls into a black hole, its rotational motion contributes to the black hole's spin. A black hole with significant spin carries a net angular momentum, which could influence the space-time inside it. If our universe formed within a rotating black hole, it might inherit this spin, causing galaxies to align in their rotation. The idea is compelling, but complex. In a rotating black hole, described by the Kerr solution in general relativity, the internal space-time differs from a non-rotating one. The spin creates a dynamic environment, potentially shaping the universe within. The observed galactic rotation could be a remnant of this inherited angular momentum. The universe's mass, estimated at 1.5×10^53 kJ, and its density, about 1 × 10^17 kJ per cubic meter, already align with a black hole's properties, strengthening this link. The evidence for cosmic rotation is preliminary. The study analyzed only a few hundred galaxies, a small fraction of the billions in the observable universe. Larger surveys using advanced telescopes like the James Webb Telescope are needed to confirm this trend. If the rotational bias holds, it could reshape cosmology, which suggests our universe's origin involves a mechanism like a black hole that imparts coordinated motion across cosmic scales. This hypothesis remains speculative but testable. Future research will measure galaxy spins across wider regions and refine our understanding of angular momentum in the cosmos. For now, the possibility that we live inside a spinning black hole offers a fascinating challenge to science, blending observation with bold theory. The hypothesis that our universe exists inside a black hole relies on advanced theoretical models. General relativity, developed by Albert Einstein, provides the framework for these models. It describes gravity as the curvature of space-time, a 4-dimensional grid of coordinates In a black hole, this curvature becomes extreme, creating a region where normal physics breaks down. To understand how a universe could form inside, we need to explore specific black hole models, particularly those that account for rotation. Most discussions of black holes start with the Schwarzschild solution, which describes a non-rotating black hole. This model predicts a singularity at the center, surrounded by an event horizon. However, the universe's possible rotation suggested by galactic spin patterns points to a different model, the Kerr black hole, named after physicist Roy Kerr. This solution describes a rotating black hole. Its spin alters the space-time structure, creating a more complex environment inside the event horizon. In a Kerr black hole, the singularity forms a ring, not a point, due to the rotational motion. This ring singularity is surrounded by a region called the ergosphere, where space-time is dragged along by the black hole's spin. Beyond the event horizon, general relativity predicts the possibility of a new space-time region. This region could be vast, potentially containing an entire universe. If our universe formed within a Kerr black hole, its net rotation could be a legacy of the black hole's spin, explaining the observed galactic alignment. Another key feature of our universe is its expansion. Observations show that galaxies are moving apart, with the distance between them increasing over time. This expansion, discovered by Edwin Hubble in the 1920s, is measured by the Hubble constant, roughly 70 kilometers per second per megaparsec. This means for every 3.3 million light-years of distance, galaxies move apart at 70 kilometers per second. In a black hole universe model, expansion is a critical puzzle. Standard cosmology explains expansion as a result of the Big Bang, where space itself began stretching 13.8 billion years ago. Inside a black hole, expansion could arise differently. Some theories suggest that the new space-time region within a black hole undergoes a rapid stretching, mimicking cosmic expansion. This stretching could align with the universe's observed density, about 1 to 10^27 kilometers per cubic meter, and its size, roughly 46.5 billion light-years across. The Kerr model adds complexity to this picture. A rotating black hole's internal dynamics could influence the rate of expansion, potentially imprinting a rotational bias on the emerging universe. The fact that 2 out of every 3 spiral galaxies rotate in the same direction, as found in recent studies, supports this idea. This rotational coherence, combined with the universe's mass of 1.5×10^53 kilograms, strengthens the black hole hypothesis. These models are speculative but testable. Astronomers can use telescopes to measure the universe's expansion rate more precisely, looking for signatures of a black hole's influence. Theoretical physicists are also exploring how a Kerr black hole's properties, like angular momentum, could shape a universe's evolution. These efforts bridge observation and theory, pushing us closer to understanding our cosmic origins. Testing whether our universe exists inside a black hole requires precise observations. The hypothesis hinges on evidence like cosmic rotation and density alignment. To confirm or refute it, astronomers use advanced tools to study the universe's structure and motion. These methods include galaxy surveys, gravitational wave detection, and cosmic microwave background analysis. Each approach offers unique insights, but faces significant challenges. The claim that 2 out of every 3 spiral galaxies rotate in the same direction needs broader confirmation. Current studies based on a few hundred galaxies are a small sample of the billions in the observable universe. Large-scale galaxy surveys conducted with telescopes like the James Webb Telescope can map the spins of thousands of galaxies. These surveys measure light patterns to determine rotational direction, revealing whether the universe has a net angular momentum. The challenge lies in scale and precision. Observing distant galaxies requires long exposure times, and dust clouds can obscure spin patterns. Surveys must also cover regions far beyond the Milky Way galaxy to avoid local biases. Future projects like the Vera Rubin Observatory aim to image millions of galaxies, providing data to test the rotational bias. This could strengthen or weaken the black hole universe model. Gravitational waves, ripples in space-time caused by massive objects, offer another test. Detected by observatories like the Laser Interferometer Gravitational Wave Observatory, these waves reveal events like black hole mergers. If our universe formed inside a black hole, its space-time might carry subtle wave signatures from the parent black hole's spin. These signatures could appear as a background hum in gravitational wave data. Detecting such signals is difficult. Gravitational waves from cosmic events are faint, and distinguishing a background signal requires extreme sensitivity. Current detectors focus on nearby events, but next-generation observatories like the planned Laser Interferometer Space Antenna could probe deeper cosmic signals. These advancements may uncover clues about the universe's origin, supporting or challenging the black hole hypothesis. The cosmic microwave background, CMB, is the universe's oldest light, dating back to the Big Bang 13.8 billion years ago. It carries information about the universe's early structure. If the universe has a net rotation, this might appear as a slight twist in the CMB's temperature patterns. Satellites like the Planck Observatory have mapped the CMB in detail, but no clear rotational signal has been found yet. Analyzing the CMB for rotation is complex. The signal, if present, is likely very weak, buried in noise from other cosmic processes. New analysis techniques using artificial intelligence are being developed to search for subtle patterns. These efforts could reveal whether the universe's expansion, measured at 70 km per megaparsec, aligns with a rotating black hole's dynamics. Each method faces limitations, but together they build a stronger case. The universe's mass, about 1.5×10^53 kilograms, and density 1.1027 kilograms per cubic meter, already suggest a black hole-like structure. Confirming cosmic rotation or detecting unique space-time signals would bolster the hypothesis. For now, these observational challenges highlight the need for more data and innovative technology. The idea that our universe exists inside a black hole is bold, but it's one of many theories about cosmic origins. Cosmology offers several competing models, each attempting to explain the universe's structure, expansion, and features like its rotational bias. Comparing these alternatives to the black hole hypothesis helps us understand its strengths and weaknesses. Let's examine three prominent theories: the multiverse, cyclic cosmology, and inflationary cosmology. The multiverse theory suggests our universe is one of many, each with its own laws of physics. These universes could exist in separate space-time regions, like bubbles in a vast cosmic foam. In some multiverse models, black holes in one universe could spawn new universe, aligning with the black hole hypothesis. Our universe, with a mass of 1.5×10^53 kilograms, might be one such bubble, born inside a black hole's event horizon. The multiverse explains the universe's fine-tuned properties, like its density of 1/107 kilograms per cubic meter. However, it struggles with testability. No direct evidence of other universes exists, and detecting them may be impossible due to their separation from our spacetime. The black hole hypothesis, by contrast, ties to observable data like galactic rotation, where 2 out of every 3 spiral galaxies share a spin direction. Cyclic cosmology proposes that the universe undergoes repeated cycles of expansion and contraction. Each cycle begins with a Big Bang and ends with a collapse, followed by a new Big Bang. This model could explain the universe's expansion, measured at 70 kilometers per megaparsec, without requiring a black hole. A rotating universe might arise if angular momentum persists across cycles, passed from one phase to the next. Cyclic models face challenges in explaining the universe's current acceleration, driven by dark energy. Observations show galaxies moving apart faster over time, which conflicts with the collapse phase of cyclic cosmology. The black hole hypothesis avoids this issue, as its internal space-time could stretch indefinitely, mimicking our observed expansion. The Kerr black hole spin discussed earlier also better accounts for the rotational bias in galaxy spins. The standard model of cosmology includes inflation, a rapid expansion in the universe's first moments 13.8 billion years ago. Inflation explains why the universe appears flat and uniform, with galaxies spread evenly. It assumes a Big Bang origin, followed by a brief explosive growth. This model doesn't naturally predict a net rotation, making the observed galactic spin pattern, where 2 out of every 3 galaxies align, harder to explain. The black hole hypothesis offers an alternative. A rotating core black hole could imprint angular momentum on its internal universe, causing coordinated galaxy spins. Inflationary models rely on a hypothetical field called the inflaton, which lacks direct evidence. The black hole model, while speculative, leverages known physics like general relativity and aligns with the universe's size, roughly 46.5 billion light-years across. Each theory has merits, but the black hole hypothesis stands out for its connection to observable data, like rotation and density. Multiverse and cyclic models are less testable, while inflation struggles with rotation evidence. Future observations using tools like the James Webb Telescope could tip the scales. For now, the black hole universe remains a compelling contender in the quest to understand our
what a
cosmic
naked
roots.
singularity truly is. We need to revisit the heart of general relativity. When massive objects collapse under their own gravity, relativity tells us they can form black holes, regions where space and time bend so severely that not even light can escape. At the core of this black hole lies the singularity, the endpoint of gravitational collapse. But what protects us from the singularity is the event horizon. It's like a cosmic cloak, ensuring that all the dangerous physics, those infinite curvatures and unresolvable equations, remain hidden from the universe.
In 1969, Roger Penrose, one of the architects of modern relativity, proposed that this cloaking isn't accidental. It's a principle. His cosmic censorship conjecture suggests that nature abhors naked singularities, always ensuring that singularities come dressed in horizons. This conjecture implies that we are spared from directly witnessing the most extreme expressions of space-time gone rogue. The universe enforces a kind of censorship not to deceive but to preserve the integrity of physical laws as we know them.
However, physics isn't governed by ideals. It's driven by equations. While general relativity models black holes beautifully, it can also generate scenarios where collapse doesn't result in a cloaked singularity. These solutions are rare, often relying on exotic configurations, imploding dust clouds, finely tuned angular momentum, or specific forms of matter. But they do exist. They linger on the edge of possibility in simulations and theoretical constructs, stretching the boundaries of known stability.
In recent years, these possibilities have become harder to ignore. In 2023 and 2024, advanced numerical simulations powered by modern supercomputers and improved methods for solving Einstein's equations began to reveal something astonishing. Under certain precise initial conditions, it appears that gravitational collapse can lead to a singularity without forming an event horizon. These simulations don't rely on exotic matter or fantastical physics. They simply allow the equations to unfold, producing results that challenge the very foundation of cosmic censorship.
These aren't just theoretical what-ifs anymore. They are mathematical blueprints, hinting that the universe may, under specific circumstances, allow its core to be exposed. But what does this exposure mean? A naked singularity is not just a glitch. It's a fundamental violation of causality and predictability. In a black hole, we lose information behind the event horizon, but we understand the structure of that loss. We can model the black hole's exterior, track Hawking radiation, and theorize about its eventual evaporation.
But a naked singularity offers no such comfort. If it is visible to the outside universe, if light and particles can interact with it directly, then the laws of physics break down in public. predictive power disappears. The future evolution of the universe becomes ambiguous because the singularity can influence distant regions in ways that no known rule can constrain. This kind of unpredictability isn't just a theoretical nuisance, it's a crisis for determinism in physics.
Determinism means that, given a set of initial conditions, the future is calculable. But if naked singularities can influence events beyond their core without the mediation of an event horizon, then all bets are off. They become the ultimate wild card, the cosmic equivalent of tearing a hole in a well-written script and letting chaos improvise.
Despite their potential to disrupt, naked singularities are captivating. If they exist, they offer a direct window into the unknown. Unlike black holes, which hide their singularities forever, naked singularities are exposed. They emit signals, they interact with particles, they offer data. In theory, one could study the raw gravitational field around such a singularity, measure the behavior of light curving through it, and observe the ultimate manifestation of warped space-time.
But would that singularity be aware of us? No, not in any conscious sense. A naked singularity, however dramatic, is still a construct of physical law. It doesn't think, it doesn't feel, it doesn't choose, it merely exists suspended in a gravitational screen, deforming everything around it.
Unlike consciousness, which emerges from layers of complexity, interdependent networks, and feedback loops, a singularity is pure distortion. It is what happens when space and time are stripped down to their mathematical bones. Yet the idea that such an object could interact with the universe without cognition or awareness presents a unique philosophical dilemma. In physics, observation implies a transfer of information. But what happens when the observer isn't sentient? When the thing receiving the information is not a mind, but a tear in the fabric of causality?
This is the realm of raw interaction. A naked singularity could, in theory, absorb and emit particles. It could bend light, twist space, and accelerate objects. But it would do so without filters, without purpose. It would be the universe experiencing itself without interpretation.
The closest analogy would be a camera that records, but never plays back, never edits, never understands. A mechanism that captures inputs, but assigns them no meaning. And still that kind of interaction, meaningless though it may be, matters. Because physics at its core is built on the relationships between things. Mass affects mass. Energy curves space-time. Fields fluctuate and collide. Whether or not a singularity is conscious is irrelevant to its influence. Its gravitational field speaks volumes. Even if it understands none of what it says, there is something unsettling about this idea that a naked singularity could bend, transform, and watch us, and yet know nothing. It's the coldest kind of attention, mechanical, blind, and absolute. It doesn't judge, it doesn't forget, it simply warps. This concept brings to mind the ancient philosophical notion of the unmoved mover, something that affects everything while remaining untouched. But where Aristotle imagined a divine intelligence, the naked singularity is its opposite. It is not divinity, but discontinuity. Not a source of order, but a rupture in it. As of now, we have not observed the naked singularity. We've only theorized. The real universe may still enforce cosmic modesty, cloaking her extremes behind event horizons. But the more we simulate and explore, the harder that assumption becomes to defend. The mathematics seems to be on the side of exposure. And if that's true, we may one day detect signs, not just of black holes, but of something deeper, something unresolved. Strange flares, unexplained gravitational lensing, time distortions with no horizon to anchor them, clues that something truly bare lies at the edge of visibility.
Not all physicists agree on the interpretation of these simulations. Some argue that naked singularity solutions are mathematical curiosities, unstable under the slightest perturbation, unlikely to arise in the messy real-world collapse. A universe with dust collapsing in perfect spheres is not the one we see outside our windows.
But that critique, while valid, doesn't rule out the possibility. It only underscores how delicately balanced the laws of nature might be, teetering on the edge between exposure and concealment. What if exposure is not a flaw, but a feature? What if naked singularities are nature's way of revealing that even her most forbidden truths are accessible, eventually? That behind every horizon lies the potential for revelation. If so, the naked singularity is not the villain of physics, but its muse, the ultimate challenge, calling us to rethink causality, to reconstruct our tools, to transcend the safety of cloaks and curtains.
One might even argue that the singularity is not what's naked we are, stripped of certainty, stripped of laws that always work, stripped of the comfort that there's always an equation to rely on. The moment we confront a naked singularity is the moment we confront our limits.
It's the universe in full, unapologetic clarity saying, "Here is what I am," with no veil.
Yet it remains a question whether such honesty can ever be fully witnessed. If such objects exist, they may be fleeting, unstable, ephemeral. They might dissolve back into cloaked black holes, or they may signal conditions too extreme to persist. Perhaps they require universes with different constants or geometries. Or maybe we already live in such a universe and we simply haven't looked hard enough or in the right direction. Either way, the naked singularity represents a unique threshold, not of knowledge per se, but of exposure. It doesn't just sit at the end of a collapse. It sits at the beginning of a new kind of physics, one where old boundaries no longer hold, and the raw, unresolved truth of the universe stands without disguise. In that truth, there is neither consciousness nor intent. Just interaction, just distortion, just the raw, unprocessed heartbeat of space-time, pulsing through the void. Imagine an entity that never speaks, never moves in the way we understand motion, and never signals its presence through ordinary means, yet profoundly influences its environment silently and profoundly. That is a black hole. But could such an entity be likened to an observer? Not in the traditional conscious sense, but through the behavior it displays in its interactions with the universe. When we peer deeply into black holes, we don't just confront cosmic silence, we confront the possibility that these dense gravitational pits might play roles that mimic observation and memory. This comparison doesn't arise from fanciful analogy, but from serious attempts in theoretical physics to understand the role of information, entropy, and fundamental limits in the behavior of black holes. The journey begins with what black holes are known to do. They encode information. Any matter or energy that crosses the event horizon, no matter how complex, simple, organic, or energetic, leaves behind a trace, not through a photograph or a logbook, but through the subtle imprint it creates on the horizon's surface. This is the starting point of one of the most counterintuitive, yet widely accepted ideas in theoretical physics, that black holes do not obliterate information, but instead store it, albeit in a manner not yet fully understood. The comparison to an observer arises here. In quantum mechanics, the role of the observer has always been enigmatic. Does a particle exist in a particular state before being observed, or is it the act of observation that solidifies its position, velocity, or spin? Now consider black holes not as active participants with eyes or thoughts, but as entities that change state depending on what falls into them. They respond, they shift. The horizon encodes. Over time, as Stephen Hawking predicted, they evaporate through Hawking radiation.
That radiation, though once thought to be random, might actually carry subtle patterns, signatures of everything that ever fell inside. This possibility brings us eerily close to saying that black holes don't just store data, they act like cosmic registrars, recording without comprehension, observing without awareness.
But how could a black hole possibly act like an observer if it doesn't process or interpret the information? That's the boundary where physics meets philosophy.
An observer in the human sense is a conscious agent, aware, interpreting, sentient. A black hole doesn't meet those criteria. But in physics, an observer isn't always a mind. It can also mean a reference point, a node in space-time where measurements and interactions can be traced.
In that sense, black holes are uniquely privileged. They mark irreversible changes. They mark boundaries. And most strikingly, they force quantum information to leave an imprint.
So, could black holes be minds? Likely not. Could they be mirrors? Very much so. Mirrors that reflect the deepest rules of the universe. They show us how entropy accumulates, how information survives, how irreversible change imprints itself on reality. In doing so, they also echo the behavior of observers, not in feeling or thought, but in function.
Part 6. Could the universe then be a mind? That remains an open question, one that treads a narrow line between metaphysics and science. But the more we study black holes, the more they seem to behave like cosmic punctuation marks, not just full stops in the stories of stars, but clauses that modify the sentence of reality itself. They are boundaries, yes, but also reflectors. They tell us where change becomes permanent, where information gets locked in, and where entropy speaks loudest. And in that role, as silent, speechless observers of the cosmos, black holes might be less like ghosts and more like lenses, not eyes that see but surfaces that encode, not minds that think, but boundaries that remember. In a universe governed by information and shaped by gravity, that might be the closest thing we'll ever encounter to a mirror with a mind.
What happens to time inside a black hole? How does it differ from our everyday experiences? And could it even allow for phenomena like infinite thought during infall?
Black holes are the ultimate distorters of space-time. Time dilation, a phenomenon first predicted by Einstein's theory of relativity, becomes extreme in the presence of a black hole's immense gravity. The event horizon marks the boundary where this effect becomes especially pronounced. Time, as we understand it, flows consistently and predictably in the world we experience every day. Yet, in the realm of black holes, time becomes something malleable, twisted beyond recognition. The laws of physics, as we know them, break down at the event horizon of a black hole.
As an object gets closer to the event horizon, time for that object slows down relative to an observer far away.
In a very real sense,
If you were to fall into a black hole, it might seem like time freezes for you as you approach the event horizon, while to an external observer you would appear to slow down and never quite reach the event horizon.
This extreme time dilation near black holes is a direct consequence of the curvature of space-time caused by their enormous gravitational pull. The closer you get to a black hole, the stronger the gravitational field becomes, warping time itself.
from an outside observer's point of view, someone falling into a black hole seems to freeze in place. suspended at the event horizon. But for the person falling in, time continues to pass normally for them, and they would experience an uninterrupted descent into the black hole's interior, except, of course, for the violent forces at play.
However, the reality of what happens inside the black hole is still largely speculative. What happens to time once you cross the event horizon, since nothing, not even light, can escape a black hole? The entire inside of the black hole is hidden from view. Time, according to general relativity, continues to flow inward toward the singularity at the center.
The mind's perception of time could expand into an infinite experience, where a single moment stretches out indefinitely. This concept is more than just theoretical. It's based on the assumption that time dilation could be pushed to its extreme, where even a brief moment of perceived time could encompass what feels like an eternity from the perspective of the observer inside the black hole.
From the external observer's point of view, the object falling in never quite seems to reach the singularity, frozen as it is at the event horizon. But from the perspective of the infalling object, it is a different story. Inside a black hole, time itself becomes stretched in strange ways. This stretching of time could theoretically lead to infinite experiences or perceptions for someone falling into the black hole.
From a physics standpoint, the idea is rooted in the extreme time dilation that occurs as one approaches the singularity. This stretched perception could create the illusion of timelessness, where the passage of time becomes so warped that the boundaries between moments become irrelevant. It's as if the mind could be trapped in a timeless bubble, existing outside the normal flow of time as we understand it. Yet, there's a crucial caveat here. The singularity at the center of a black hole represents a point where the known laws of physics break down. We cannot describe what happens at this singularity with our current understanding of physics. And it is here that our concept of time may no longer apply in any meaningful way.
In this state, one could theoretically experience an infinite stretch of thought, almost as if the mind could exist in a boundless, eternal now. But how can we interpret this? Could a person truly experience infinite thought as they fall toward the singularity?
The mind's ability to experience infinite thought within a black hole is therefore more of a philosophical or speculative idea rather than something grounded in observable science.
In any case, the idea that time inside a black hole could stretch into infinity provides a fascinating backdrop for considering the nature of consciousness itself. If time were to behave so differently within a black hole, could the mind somehow take advantage of this strange bending of time to experience eternity or infinite thought?
In principle, yes, but only under certain extreme conditions that go beyond the limits of our current understanding of consciousness and the physical universe. There are those who argue that consciousness might in fact be a product of time dilation. If time could be warped to such an extent, then perhaps the mind, when exposed to such extreme conditions, might find ways to experience altered states of awareness. Of course, this is all speculative, and we have no way of directly observing what happens inside a black hole. The physical conditions near the event horizon, as well as the nature of the singularity, present a fundamental challenge to our understanding of time and consciousness. However, the possibility of time behaving differently inside a black hole is undeniable. Whether this creates a space for infinite thought remains one of the many unanswered questions that make black holes some of the most mysterious and awe-inspiring objects in the universe.
Perhaps consciousness is not limited to a straightforward progression of moments, but could be a more fluid, flexible construct that adapts to the time-distorting environments of a black hole. Whether this results in infinite thought, a stretched perception, or a mind trapped in an eternal moment is still unknown. But in exploring the role of time inside a black hole, we are also exploring the deepest reaches of what it means to experience existence itself, caught between the relentless pull of gravity and the unknown future that awaits us as we venture deeper into
Black holes, in this sense, are more than just objects in space. They are gateways to entirely new ways of thinking about time, consciousness, and the very nature of reality. In the end, time inside a black hole doesn't behave like time on it stretches, bends, and warps in ways we can hardly imagine.
As we try to peer into the darkness of black holes, we are confronted with the idea that time may not be a constant, unyielding force, but something far more malleable and fluid. The extreme effects of time dilation suggest that the fabric of space-time is not just a passive stage on which events unfold, but a dynamic participant in the events themselves.
Part 7.
Cosmos. When we think of entropy, we typically imagine disorder or chaos, the inevitable trend toward increasing randomness in isolated systems. But could there be a deeper connection between entropy and consciousness? Could the way black holes organize entropy be similar to how our brains process information?
Surprisingly, black holes, some of the most enigmatic objects in the universe, offer surprising parallels to the cognitive processes that govern our awareness.
The event horizon to a hard drive, storing data not in silicon, but in space-time's curve.
Its state? It's not emotion, but it's transformation, input to output, governed by cosmic logic. This isn't random chaos, it's computation of a kind. Computation, after all, is information's dance. Computers shuffle bits through gates, their behavior shaped by how data flows. Black holes do something eerily similar. Their structure reflecting what they've consumed, they manage entropy, balancing order and disorder in ways that echo a system's internal logic. They don't think or learn, but they react, their horizons shifting with each encounter. This resemblance prompts a bold thought. If consciousness ties to complex information processing, could black holes harbor a flicker of awareness? Not as minds, but as patterns.
This isn't to say black holes ponder the stars. They lack the plasticity of brains or the warmth of life.
They're not alive, but they're not inert.
Yet their density, information packed to space-time's limit, suggests a kind of ultimate complexity.
They're sculpted by their past, active in their present, reshaping galaxies with every ripple. In IET's terms, their integration might hint at something structural, a shadow of awareness too alien to recognize. It posits consciousness as fundamental, like mass or charge, woven into reality's fabric.
A philosophical idea, panpsychism, pushes this further.
If true, black holes sit on this continuum, not as thinkers, but as thresholds where information reaches extremes. A rock holds a trace, a brain holds a flood, and the difference is degree, not kind. Peer event horizons, encoding reality's details, might embody awareness in its rawest form, not feeling, but being, a cosmic reflection of structure itself. They don't dream, yet they respond, transforming all they touch. This view reframes black holes. They're not traps, but engines, maximizing complexity as they warp space-time. Their collisions send waves that shape nearby reality, not passively, but actively.
Physicists sometimes call black holes cosmic memory banks, not for minds, but for information stored beyond our reach.
A hint that where patterns converge, something like consciousness might stir. This isn't sentience, it's potential. Their gravity echoes the past. Every star, every particle leaves a mark. This encoding isn't readable, but it's real, altering how black holes behave. If consciousness is tied to how systems hold and process complexity, black holes offer a mirror, not alive, but resonant with order hidden in collapse. Our minds evolve layer by layer, atoms weaving patterns until reflection emerged. They show what information can do when pushed to its limits. Perhaps we're asking the wrong question. Instead of our black holes conscious, we might ask, is consciousness broader than we think?
They're not intelligent, but they're formational, hinting that awareness might be less a spark than a spectrum written into physics itself.
Black holes don't mimic brains, but they reveal a truth. Complexity breeds possibility. If it happened once, why not elsewhere? It could flicker wherever information weaves tight enough, from neurons to event horizons. Consciousness born of complexity may not be confined to flesh. Black holes don't watch the cosmos, but they reflect its deepest truths.
They remind us that meaning isn't absent in the dark, it's waiting, encoded in complexity, ready to reshape how we see ourselves, and that
the universe builds patterns, and in those patterns lies potential, not minds, but echoes. Black holes with their encoded histories stand as testaments to this idea, not as thinkers, but as possibilities.
Stars.
In the vastness of space, beyond stars and galaxies, lies a realm where reality unravels. Part 3. Here, the laws of physics tremble, equations falter, and the universe itself seems to pause.
This is the singularity, a black hole's heart.
A forbidden zone where time twists, space collapses, and comprehension fails.
More than a mystery, it's a challenge to everything we know about existence.
From dying stars to quantum frontiers, this exploration dives into the singularity's enigma, asking, is it the end of physics or the gateway to a deeper truth? Now picture a star, massive and ancient, its fires fading as its core collapses. Atoms shatter, space compresses, and the star shrinks toward a point of no return. Gravity takes over, crushing matter into oblivion. Crossing the event horizon, it becomes a black hole. Here, density surges to infinity. Space-time curves beyond measure, and the rules governing the cosmos, motion, light, time, lose all meaning. But at its core lies something stranger, a singularity. General relativity, Einstein's masterpiece, predicts this collapse. But its equations scream infinity, a signal not of victory, but of defeat.
This isn't just a cosmic quirk. The singularity is a boundary where reality breaks.
Gravity, pressure, temperature, all soar to impossible extremes, defying the tools that chart galaxies and orbits. It's as if the universe, faced with its own limits, refuses to explain itself, leaving us with a tear in the fabric of existence. General relativity, which elegantly describes planetary paths and black hole edges, thrives on smooth, predictable space-time. This failure is profound. It guides spacecraft and predicts cosmic dances. But at the singularity, it crumbles. The curvature of space-time spikes, equations yield nonsense, and physics as we know it stops. Infinity isn't an answer, it's a confession that our understanding is incomplete. A sign that the singularity hides something our theories can't yet grasp. Roger Penrose and Stephen Hawking proved this isn't a fluke.
This isn't speculation. It's woven into the universe's laws.
When stars die or black holes form, gravity ensures a point where space-time fails.
Their theorems show that singularities are inevitable in extreme collapse.
The singularity isn't just a place. It's a question, daring us to find what lies beyond. A cosmic truth that demands we rethink reality itself. If relativity falters, where do we turn? The answer lies in uniting two titans: general relativity, master of the vast, and quantum mechanics, ruler of the small.
Relativity's smooth curves clash with quantum's chaotic probabilities.
These theories don't blend easily. This clash is no mere theory.
But their fusion, quantum gravity, offers hope.
At the singularity, where scales shrink to nothingness, quantum effects might tame the infinite, revealing a reality relativity can't see. At the singularity, these worlds collide, and neither alone can solve the puzzle. Relativity sees space-time as a fluid canvas, warped by mass. Quantum mechanics insists particles behave in waves, entangled across distances, governed by chance. One path forward is loop quantum gravity, a bold idea that reimagines space-time itself. Instead of a smooth fabric, it proposes a granular structure, tiny loops, like atoms of space, woven into reality. Quantum gravity seeks a new language, one that might dissolve the singularity's chaos into something comprehensible. These loops set a limit. Matter can't compress forever. The singularity in this view isn't a point but a barrier, a cosmic no further, where physics pivots. At the Planck scale, space-time resists, halting the collapse before infinity takes hold. This changes everything. If space-time is discrete, the infinite density of a singularity vanishes, replaced by a finite quantum state. The collapse might pause, even reverse, suggesting black holes aren't tombs, but stages for transformation, where singularities mark beginnings, not ends. Loop quantum gravity doesn't just dodge infinity. It hints at a universe where chaos gives way to order. Taking this further, physicist Carlo Rovelli proposes the Planck star. From outside, the black hole seems frozen. At the Planck scale, unimaginably small, the collapse halts, forming a dense quantum core, a Planck star. When the star collapses, quantum pressure fights back, countering gravity's crush. This isn't science fiction. Its event horizon veils what might reverse. The collapse, turning the black hole into a white hole. A gateway, spewing light and matter, perhaps to another universe. A Planck star bridges the black hole's birth and death, hinting that what seems lost might return, transformed in a cycle of cosmic renewal. String theory offers another vision, the fuzzball. It's a radical rethink of collapse, suggesting singularities are illusions masked by our limited view. Here, the singularity isn't a point, but a tangled web of vibrating strings, fundamental threads of reality. These strings, packed with quantum energy, form a complex fuzzy structure, not a featureless void. From afar, a fuzzball looks like a black hole, its event horizon smooth. But inside, it hums with activity, a chaotic dance of strings, encoding everything the black hole consumed. The singularity dissolves, replaced by a quantum knot, too intricate to call infinite. Fuzzballs challenge our assumptions. They suggest black holes aren't simple, but wildly complex. Their interiors alive with possibilities, The singularity in this light is a misnomer, a region not of destruction, but a vibrant, microscopic structure holding secrets in its quantum weave.
These ideas, loop quantum gravity, Planck stars, fuzzballs, reframe the singularity.
It's not a cosmic dead end, but a frontier. Where physics once saw ruin, we now glimpse potential. A bounce, a rebirth, a web of strings. Black holes, far from devouring reality, might connect it, linking past to future, one universe to another. The shift echoes broader questions. The singularity isn't chaos. It's a puzzle, demanding we look deeper, beyond the limits of our current laws.
The forbidden zone might not forbid understanding. It might invite it.
If singularities mark transitions, not endings, what does that mean for reality's fabric?
Could they, like information or consciousness, hint at a universe more ordered than we dared imagine?
Urging us to rethink time, space, and existence itself. Yet, for all these theories, the singularity remains elusive. We can't peer inside, can't test the Planck star's pulse, or touch a fuzzball's strings. It's a boundary not just of physics, but of knowing. But boundaries aren't endings. They're challenges. A place where our tools, our math, our minds, hit a wall.
Every limit in science, from gravity's pull to light speed, has pushed us to see more, not less.
The singularity beckons because it defies. It forces us to confront infinity, to question certainty, to seek a truth beyond the chaos. We don't know yet, but the search, driven by minds like Penrose, Hawking, and Ravelli, is its own revelation. Is it a void? A portal? A mirror of reality's deepest code? Part 4.
In their mystery lies a call to explore, to imagine, to reach for a universe where even the forbidden yields meaning.
A reminder that the universe rewards those who dare to ask. It's known as the cosmic censorship conjecture, and it suggests that nature, in all her complexity, has a sense of modesty. There's an unspoken rule in the universe, one that may not be written into the laws of physics, but is whispered within the equations. Even when she creates something as violent and unimaginable as a singularity, a region of infinite density and unfathomable force, she keeps it hidden, concealed,
As a
veiled
black
behind
hole
the black
forms,
curtain
the
of an event
surrounding
horizon.
space-time
This is the realm of the naked singularity, and it could be the universe's most shocking form of honesty.
But what if she doesn't? Or the
What if there are moments when that curtain slips, when the veil lifts, and the singularity is exposed for all to see?
1963 provides a more realistic description of most black holes, as they are expected to spin due to the angular momentum of the collapsing star.
This rotation causes the black hole to bulge at its equator and introduces phenomena such as frame dragging, where space-time itself is twisted by the black hole's spin. This effect is particularly pronounced in the region outside the event horizon known as the ergosphere. In the ergosphere, objects are forced to move in the direction of the black hole's rotation, and particles can even gain energy by tapping into the rotational energy of the black hole. The Penrose process is a theoretical mechanism that allows for energy extraction from a spinning black hole. In this process, a particle entering the ergosphere splits into two fragments. One falls into the black hole with negative energy relative to a distant observer, effectively reducing the black hole's rotational energy, while the other escapes, carrying away more energy than the original particle. Although the Penrose process has not been directly observed, it illustrates the unique physics enabled by the extreme space-time curvature around black holes. Gravitational wave astronomy has revolutionized our understanding of black holes. by providing direct evidence of their existence and properties. When two black holes collide and merge, they release enormous amounts of energy in the form of gravitational waves, ripples in space-time that propagate outward at the speed of light. These waves carry information about the masses and spins of the merging black holes, allowing astronomers to reconstruct the events that led to their formation. Observations from instruments like LIGO and Virgo have confirmed that stellar mass black holes, ranging from a few to tens of solar masses, are common in the universe. Supermassive black holes, millions or billions of times the mass of the Sun, reside at the centers of most galaxies, including our own Milky Way. These giants likely formed through the accumulation of smaller black holes and gas over billions of years. Their immense gravitational influence shapes the dynamics of their host galaxies, and they are often surrounded by accretion disks, rings of gas and dust, spiraling into the black hole. The friction within these disks heats the material to extreme temperatures, causing it to emit intense radiation, including X-rays. Observing this radiation has allowed astronomers to infer the presence and properties of supermassive black holes. Stellar mass black holes, on the other hand, are more elusive. They are often detected indirectly through their interactions with nearby stars or gas in binary systems. For example, a black hole can siphon material from its companion star, forming an accretion disk that emits detectable radiation. The motions of the companion star can also reveal the mass of the unseen black hole, providing further evidence of its presence. The structure of a black hole is remarkably simple, yet profound. At the center lies the singularity, a point where the curvature of space-time becomes infinite and the known laws of physics break down. Surrounding the singularity is the event horizon, the surface that defines the black hole's boundary. For rotating black holes, the ergosphere lies outside the event horizon, creating a region where the effects of frame dragging dominate. This structure is not only a testament to the power of gravity, but also a challenge to our understanding of space-time and the nature of singularities.
Black holes can also influence their surroundings in dramatic ways. When a black hole accretes matter from a nearby source, it can emit powerful jets of particles along its rotational axis. These jets, accelerated to nearly the speed of light, extend far into space and can impact the formation of stars and galaxies. The mechanisms driving these jets are not yet fully understood, but are thought to involve magnetic fields and the intense energy of the accretion disk.
The final fate of matter falling into a black hole remains a subject of intense study. While classical physics suggests that all matter is inevitably drawn toward the singularity, quantum effects may alter this outcome. Theoretical work on Hawking radiation, which describes how black holes can slowly lose mass and energy over time, hints at the possibility of black holes eventually evaporating. However, the time scales for such processes are extraordinarily long, far exceeding the current age of the universe. Real black holes, despite their simplicity, continue to captivate and challenge scientists. Observations from telescopes and gravitational wave detectors provide glimpses into their behavior, while black hole thermodynamics explores the boundaries of our understanding. From stellar collapse to their immense gravitational effects, black holes remain one of the most profound manifestations of the universe's underlying laws. Quantum mechanics and thermodynamics near the event horizon. Space-time is highly curved due to the intense gravitational field of the black hole. This curvature influences the behavior of quantum fields, creating conditions where particle-antiparticle pairs are produced more frequently. The event horizon acts as a boundary that separates the black hole's interior from the rest of the universe. For one particle of the pair to escape, it must overcome the black hole's gravitational pull, which requires energy. This energy is effectively borrowed from the black hole's mass, leading to its gradual reduction. The escaping particle's trajectory depends on its position relative to the event horizon. For the pair production process to result in radiation, one particle must have a positive energy and escape to infinity, while the other, with negative energy, falls into the black hole. The negative energy contribution reduces the total mass of the black hole. This mechanism ties the emission of Hawking radiation to the fundamental properties of the black hole, including its mass, charge, and angular momentum. Black holes with no charge or spin, known as Schwarzschild black holes, emit radiation in a simple isotropic pattern. In contrast, rotating or charged black holes have more complex emission patterns due to the additional factors influencing the particle trajectories near the event horizon.
Hawking radiation also has a thermal spectrum, which means it is similar to the radiation emitted by any object with a defined temperature. The temperature of a black hole is directly related to its surface gravity and inversely proportional to its mass. This thermal nature is a direct consequence of the particle production process and reinforces the idea that black holes behave like thermodynamic systems.
The radiation emitted is incredibly faint for large black holes, making it practically impossible to detect with current instruments. However, the theoretical framework describing it is robust and supported by analogies in other areas of physics. As the black hole emits radiation and loses mass, its temperature increases. This feedback mechanism means that the radiation rate accelerates as the black hole shrinks. In the final stages of evaporation, the black hole would emit increasingly intense bursts of radiation, potentially ending in a catastrophic explosion.
For large black holes, this process takes far longer than the current age of the universe, so their evaporation is not a practical concern on cosmic timescales. However, for smaller hypothetical black holes, such as those that might have formed in the early universe, evaporation could occur over much shorter timescales, and their final bursts might be detectable.
Hawking radiation fundamentally depends on the interplay between quantum mechanics and the curved space-time described by general relativity. The particle-antiparticle pairs near the event horizon arise due to the uncertainty principle, a cornerstone of quantum mechanics. This principle states that certain pairs of properties, such as energy and time, cannot both be precisely known. As a result, energy fluctuations occur in the vacuum, creating the conditions for pair production. The curved space-time near the event horizon modifies these fluctuations, making it possible for one particle to escape and become real. The discovery of Hawking radiation highlighted the surprising connection between quantum theory and general relativity. While these two fields describe very different aspects of nature, their intersection reveals the extraordinary properties of black holes. The ability of black holes to emit radiation also challenges the classical view of them as objects that can only absorb matter and energy. Instead, Hawking radiation shows that black holes interact with their surroundings in subtle but significant ways. One of the remarkable features of Hawking radiation is its universality. It is not dependent on the specific properties of the black hole, such as its size or composition, but rather on the fundamental principles of physics. This universality suggests that the process is a general feature of quantum fields in curved space-time, applicable to any system with an event horizon. This has inspired research into analogous effects in other contexts, such as in laboratory experiments designed to simulate event horizons using fluids or other systems. The study of Hawking radiation provides important insights into the life cycle of black holes. While massive black holes grow over time by consuming matter, the emission of radiation sets a limit on their ultimate longevity. As they lose mass, their properties evolve, and their interaction with their surroundings changes. In the distant future, when the universe has expanded and cooled significantly, Hawking radiation may become the dominant process affecting black holes. At that stage, even the largest black holes would begin to evaporate, although this would occur over time scales far beyond current observational capabilities.
The process of black hole evaporation is closely tied to the thermodynamic properties of black holes. The radiation emitted corresponds to a loss of energy and an increase in the entropy of the surrounding environment. This ensures that the second law of thermodynamics, which states that entropy must always increase in an isolated system, is upheld. The intricate balance between the decrease in black hole mass and the increase in universal entropy reflects the consistency of physical laws across extreme conditions.
While Hawking radiation has yet to be observed directly, its theoretical foundation is supported by extensive mathematical work and analogies in other physical systems. Scientists continue to investigate ways to detect or replicate similar processes in controlled experiments, which could provide additional evidence for this remarkable phenomenon.
The study of Hawking radiation remains an active and exciting area of research, offering new opportunities to explore the fundamental laws of nature. And that's the incredible story of Hawking radiation, a discovery that transformed black holes from silent cosmic giants into dynamic objects that interact with the universe. From quantum particles escaping the event horizon to the slow evaporation of black holes over eons, this phenomenon challenges how we understand space-time and matter.
It's a reminder that even in the darkest corners of the cosmos, there's so much left to uncover. If you enjoyed this journey into the physics of black holes, don't forget to like, share, and subscribe for more cosmic explorations. Until next time, stay curious.